Welcome to Team 1's final presentation for RS 557, the Mirai project. Our goal was to bridge the gap between simulation and reality by investigating a specific question. How does a variable spine length dictate the behavioral stability of segmented robots? Using MuJoCo, we conducted a parametric sweep on the intersegment length L to optimize the robot's geometry. The simulation revealed a critical trade-off. Short spines of length less than 50 caused mechanical interference between legs, while long spines of length more than 70 increased the rotational inertia, leading to excessive yaw or wiggling during forward motion. To validate these behaviors, we fabricated a variable length chassis using the SEM process and integrated an onboarded IMU to collect real-time data. This allowed us to map the robot's physical response against the simulation predictions. Crucially, the physical robot replicated the specific behavioral regimes we identified in MuJoCo, just as the simulation predicted. Varying the spine length in the real world directly altered the robot's stability profile, confirming the theoretical trade-off between leg influence and rotational inertia. The IMU data serves as proof that our simulation accurately captured how spinal geometry dictates dynamics in reality. Ultimately, Myriad demonstrates that stability isn't just about control algorithm, it's about intelligent design. It takes more unstable from moving forward. By validating our models in real world, we have proven that a tuned compliant structure is the key to robust locomotion. More information about our project can be found on our project website. We can download the full report, which has detailed explanation of our inspiration, methodology, goals, experimentation, and results. The website also talks about the um, motivation, goals, the introduction to our project, the synthesis of morphological structures, biological inspirations, and our robotic design as well. In the robot design, we moved away from rotating legs to implementing Jansen's linkage, where each linkage's length is defined by the Holy number. This linkage converts rotary motion into stepping guide with high ground clearance. The robot is built using SEM. Think of it as engineering origami. We laser cut rigid cardstock, flexible material, laminated them into a single 5-layer sheet that folds up into a 3D robot. The heart of our robot is the parallel articulated spine. Unlike a rigid brick, this compliant backbone allows the robot to twist and bend. We can actually tune the stiffness and length of the spine to change the robot behavior and to see how it turns and stabilizes itself at different lengths. The fabrication process included cardstock as a rigid layer, adhesive, which was heat sealed, and flexure material. The workflow began in LibreCAD, where we designed the cut structure and used the Foldable Robotics library to generate cut files. Later, we used laser machines, heat seals, 3D printers, and glue guns to manufacture and fabricate the process. Over multiple iterations, we 3D printed custom motor modes, spine beam designs, and switched to a thicker flexure material to avoid buckling. Before building, we simulated the model in MuJoCo. We set the following parameters: the time step plus 0.001, RK4 integrator, zero point 0.5 friction, 5 as the motor gain. We then later optimized these parameters and identified the optimal values for each material. We then validated this material by implementing it on a physical robot where we experienced similar results, where the optimal length of about 50 to 60 gave us more stable robot motion, locomotion compared to having lesser than 50 to 60 of spine length or greater than 70 of spine length. We also have an update on our project one report. This report can also be downloaded through the website, and the details of the report are mentioned on the website. We also have a GitHub which explains all the code that we used for this project. Opening GitHub, you can see multiple branches, and each branch performs a specific feature. For example, the cut file generator has an IPYNB file and a README file. The README file explains about what the files are, the file structure is, and the IPYNB file explains the code itself. Similarly, we can check the code for motor control, where we have IMU data streaming and motor control in the main.py. MuJoCo simulation branch talks about MuJoCo, how we implemented a reinforced learning agent into MuJoCo simulation, how we got parameters from that simulation, and how we transferred the parameters into real world. Finally, we have project draft one, which talks about our initial submission for the team assignment one, and we have the code for the website in the website branch. From simulation to fabrication to experimental validation, this project demonstrates complexities of bio-inspired designs. You can download the full technical report directly from our homepage to get more information, or visit GitHub to get more idea about the code. Thank you.